In Cluster 11 Introduction to Autonomous Vehicles, we built our own robots and trained them to drive autonomously. The first tool we used to drive our robots autonomously was called Donkey Car.
Donkey Car is a no-frills and widely used open-source framework for autonomous driving. That's why it is named after the reliable but humble donkey. There are a variety of ways to drive autonomously using Donkey Car, but the first technique we implemented was behavior cloning.
Behavior cloning is a technique that uses a deep neural network to clone or copy the behavior of a human driver. The robot collects image data, steering direction, and throttle value to make generalizations about how a human drives and learn to reproduce this result.
Before taking our physical robots to the track, we set up Donkey Sim, which is an AI gym that allows us to collect data and train a virtual robot. It looks a lot like a video game, but the virtual robot is collecting real data. The better you drive, the better your AI model will be.
We set up a virtual machine to run Donkey Sim. A virtual machine is a software program that creates a simulated computer system within your actual physical computer.
A virtual machine allows you to run an entirely separate operating system virtually. Virtual machines are important because software often relies on dependencies that we want to account for by giving everyone the same development environment. We use this virtual machine to install software on our physical robots later as well.
Within our virtual machine, we learned how to SSH, which stands for Secure Shell, into a powerful GPU cluster at the San Diego Supercomputer Center. Once our data was transferred to the GPU cluster, we trained an AI model to use in our simulator and drive the robot autonomously.
We learned in the process containerization tools like Kubernetes and Docker, which are necessary for setting up proper dependencies and powerful tools for cloud computing applications.
Getting our physical robots set up required us to learn CAD, or computer-aided design. We used the CAD program Onshape to design our robots' baseplates and camera mounts.
We used the tools available to us in the Makerspace at UC San Diego. This is a state-of-the-art facility at the Design and Innovation Building with laser cutters that allowed us to cut our baseplates from acrylic, and 3D printing machines, which we used to build our robots' camera mounts.
We learned the wiring for our robots using a circuit diagram and connected remotely via SSH to the Jetson Nanos that ran our robots. These Jetson Nanos are single-board computers that run embedded Linux and operate as the brain of our robots.
These robots, like those in the simulator, collect image, steering, and throttle data so we can train an AI model to clone our behavior. At Lake Miramar, we use GNSS, which is similar to GPS, to get our robots moving autonomously without any help from the camera.
GNSS waypoint tracking leverages the high-performance wireless education network, which has a station at UC San Diego to get highly accurate GNSS positioning.
Our robots are then able to determine the precise location, even though traditional GNSS or GPS data will provide satellite error of a few years.
By manually driving our robots and leaving waypoints that form a path, we learned how to program a PID controller to follow waypoints autonomously. PID stands for Proportional, Integral, and Derivative Control.
The proportional term steers based on the error, how far off the path the robot currently is. The integral term helps with biases, like incorrect wheel alignment, and the derivative smooths things out as the robot attempts to follow the waypoints that were left behind. Without fine-tuning these controls, the robot will get off path.
As we built our robots, we researched the ethical dilemmas businesses face in the field of autonomous driving. I nominated 3 essays to represent our cluster and be judged by a panel of ethicists at the university. Later this week, the panel will inform us on what they have chosen was the best essay from our cluster. We are now moving into the final week at Cosmos, and our final projects will require us to learn about RGBD cameras and their applications for autonomous vehicles. RGBD cameras detect red, green, and blue images like most cameras, but also provide information on depth. The OAK-D-Lite cameras that we are running in our robots are state-of-the-art Edge AI devices that allow us to perform complex computer vision applications such as object detection directly on the device. This is made possible by the advanced onboard processing power of the OAK-D-Lite. Coupled with our Edge AI Jetson Nano single-board computers, we are running AI on the edge, on the edge. For our final projects, our only limitations will be our imagination and tight timeline as we develop a novel approach to autonomous driving.